I think it's recording. Okay, so let's go back. Yeah, we finished discussing the elliptic cryptography, and now let us look into different storage strategies, right? Like hot and cold storage strategies, and then I was also telling that there is hierarchical key generation and those kinds of things, right? So we will always talk about two types of storages, hot and cold storages. This is same as what you have, like for example, if you are very rich, if you have lots of money, let's say you have a couple of crores of rupees, then you don't want to carry all the money in your wallet or in your suitcase or something like that, right? It is very insecure. So what you do, you invest them in properties, or you go to the bank and put them into fixed deposit. So that is like the cold storage, where you have huge resources saved, huge kinds of huge what saved in a secure location. But on the other hand, you also need some money for your maybe daily expenses and things like that. So which you keep in your wallet and things like that are easily accessible places. So that is called the hard storage, right? So you always back and forth switch between the cold storage and hard storage. Where you are needing money, you go to the bank and you break some of the fixed deposit and you convert into hard storage, or you can say the easily convenience money. So like that, you always navigate between the cold storage and hard storage. What is cold storage? What is hard storage, right? So again, when you come back to the cryptocurrencies, so this is nothing but the keys, right? So you have one storage, hard storage, where you have the keys, public and private keys. Similarly, you have the cold storage, which is like an offline storage. Because let's say that you have 100 bitcoins. The value of 100 bitcoins worth will be multiple crores of rupees. So you don't want to risk them losing. You don't want to let somebody steal your keys and steal the money, right? So that's why what you do is you will store in a secure place. So the best way is to store it for example, let's say that you have put it in a laptop or store it in a laptop or keys on the laptop. Then it is like putting the laptop into a very secure location, like a safe. Nobody else can access some things like that. So there are some better strategies. So what you normally do is, if you store it on an online device, for example, like a computer and things like that, you will make it offline. So you are not connected to the internet and things like that. Why? Because there is a lot of hacking happening on the internet, and people can steal the currencies. So a lot of cryptocurrency exchanges have been attacked by the hackers and things like that. So what normally you would do is you have separate hot and cold storage. Obviously, you need to have separate keys for both of them. Otherwise, the coins in the cold storage would be vulnerable if the hard storage is compromised, right? Let's say the hard storage is your laptop or your mobile phone, right? And if somebody hacks your mobile phone or laptop, and then they will also get access to the cold storage because they are connected somehow and things like that. Again, you want to connect these cold and hot storages at some point of time, because as I mentioned before, when you want to spend currency from the the coins from the cold storage, you need to transfer them to the hot storage. So that means then you need to connect them and things like that. So that's why normally what people do is they will keep the cold storage offline setting, so that they are not connected to the internet and things like that. I also teach cyber security. So many times hackings happen, and this is one of the very good link. It is a BBC podcast. I don't know how many of you heard about it. This is called Lazarus Heist. Lazarus Heist is nothing but a series of podcasts prepared by the BBC. about North Korean state-sponsored hacker group. So North Korea, it has been under financial sanctions for last 20 to 30 years, a lot of financial sanctions. But on the other hand, it is surviving because of a lot of tactics, right? They have state-sponsored hackers and things like that. So, and these are very good episodes which talk about how they hacked the cryptocurrency exchanges. So, what is a cryptocurrency exchange? Where people will have their wallets. For example, let's say that if I have some crypto coins, I will open an account in one of the exchanges. So they will, it's like keeping your coins with them, right? So it's like storing your money in a bank, right? So what happens if the bank is hacked, right? So they will steal all the money, right? So similarly, they attacked the cryptocurrency exchange in one of the cryptocurrency exchanges in Singapore, and they steal like few hundred millions of dollars or something like that. And but luckily it was recovered. And similarly, they also hacked Bangladesh National Bank. So, Bangladesh National Bank is nothing but like a Reserve Bank of India. So it is the central bank, you can say, right? And this episode, $1 billion hack, is a hacking attempt on the Bangladesh National Bank and trying to steal $1 billion. You can imagine this is a pretty big hack, right? So they tried to steal $1 billion, and out of that, I think they were able to steal. This happened in 2016. They were able to steal at least 80 to $100 million. Even then, it's a huge amount of money. So I would definitely advise you to watch this podcast. And they have a pretty big series covering different tactics and things like that. So it's really good. Of course, it's a bit, you can say it's a bit propaganda against North Korean regime and other kinds of things. On the other hand, focus more on the cybersecurity aspects and how they were able to attack the the cryptocurrency exchanges and steal the bitcoins and other kinds of things, right? So yeah, maybe watch this. Okay, so get back to the lecture again. So you have hard storage and cold storage. So again, if you have the hard storage and cold storage, you need at some point of time, let's say that you have several hundred bitcoins, you will get through the hard storage and you will store them to the cold storage. So that means you need to know about the cold addresses because you want to store them insecurely. So cold addresses are the addresses on the cold storage. So you need to transfer them here. So then you will have the money in the cold storage and you make it offline afterwards. And when you want to spend your money, and because you need to get them to the hot storage, so you will connect this to the online and you will transfer the coins from the cold storage to the hot addresses. Hot addresses are nothing but the public addresses on the hot storage side. So then you will transfer the money onto that side. So you make transfers between the hot and cold storage and things like that. So the biggest problem is, as I told you before, both these cold and hot storages is nothing but a bunch of keys, right? So you have a bunch of keys on the hot storage space, and you have a bunch of keys on the cold storage space, basically public and private keys and things like that. So at some point of time, when you want to transfer money from the cold to hot and hot to cold, so you need to know the addresses the cold storage has the money to where you have to transfer them. So even though you want to keep the cold storage offline, for example, here it is, right? So you want to keep the cold storage offline. So that means not connected to internet. But you need to know about which addresses this cold storage holds, because you need to transfer the coins from the hot storage to cold storage, right? So that is the biggest problem here. So what you do, you can use different solutions. For example, go and generate a bunch of keys, right? So let us say you want, you generate 100 public keys and 100 private key pairs on the cold storage, and transfer all the addresses to the hot storage, and or you can keep all the cold storage addresses in the hot side, and so that you can transfer the currency, right? And then make the cold storage offline. So this is an awkward solution because you have to generate a bunch of keys from the cold storage and keep them available to the hot storage, right? So that is one way of doing things. So this is called, let's call this as awkward solution. But there is a better solution, which is hierarchical wallet, which we go through one by step by step. So this is the awkward solution. So what you do is you generate both the public and private key pairs from the cold storage. Let's say you want 100, and you will generate 100 public and private key pairs, and you will keep all the private keys on the cold storage safe location and make it offline. And you take all the public keys, connected public keys, and use them on the hot storage. Right, so this is the normal solution which you can do it, but we can also do it in an elegant way using hierarchical key generation. What does it mean? So what you do is you don't generate the private keys. So on the other hand, you will do some cryptographic magic. I will show you later how that is done. Like in the case when you come to the hierarchical key generation and things like that, we will look into the algorithm a bit in depth. So what it contains and things like that. So on the other hand, what you do is you will generate some kind of address generation info. Similarly, you need private keys, right? So you will also generate private key generation info. This is not the private key, and this is not the public key. That means we are not generating the public keys and private keys right now. On the other hand, we use some cryptographic technique. We generate public key, private key generation information, and also public key generation information. This is like some kind of information which we can use to generate public and private keys, right? And then you keep this into the safe offline location, perfectly fine. And you transfer this address generation information to the hot storage. And hot storage, whenever it needs to get a new address, it simply uses this address generation information, and it passes the integer, and then it can get the new public addresses, right? So that means it will get a public key, and it can transfer the coins to there and things like that. And then let's say that we want to spend the money at some point of time from the cold storage, right? So using these addresses, all the coins are transferred to the cold storage. And then whenever we want to spend money, so now we need to go to the cold storage. We have the private key generation information. No private key is generated, only the information we have previously. And we use some technique, the same technique. We pass these respective integers, and then we will get the figure. So one good thing is, as I was mentioning before, in RSA and public key cryptography, both the public and private keys, they should be connected, right? So they are connected. Otherwise, it doesn't work, right? But in this case, let's say you pass I as 5 integer, and here also you pass I as 5, and then you will get the fifth public key here, and you will get the connected fifth private key here. So they are connected keys, you can say. This is a trick which we will do later. Any questions so far? The advantage with this is it doesn't leak the information. So even if somebody get compromised this information, like address generation information, which is needed for the public keys on the hard side, right? Even if they somehow get hold of it, they cannot simply generate the private keys from it. So that is the main security characteristics it will offer. So What we do is more, we use hierarchical wallets. Basically, they use the same strategy. So instead of generating the single addresses, we generate the generation information, public key and private key generation information, and we use an index to create the connected private keys and public keys. So this is how it works. We don't need to look into the algorithm a bit more. Okay. Let's look into several ways to store the cold storage information. I was talking about cold storage, which needs to be secure and things like that. So normally what people do is they can put the information stored in a device, either a piece of paper, printed paper, or something like that, or a mobile, you can say mobile or a laptop or some storage information or external hard disk. You store the information on a hard disk and put this hard disk in a locked safe or something like that. So that is one solution. As long as your safe is fine, then you have all the information, right? You can use Brain Wallet. So this is also we look into a bit later. You can use passphrases and mnemonic codes for remembering the codes, the keys and things like that. And you can print on a piece of paper and lock the piece of paper in a safe or something like that. Or you can also use some kind of hardware devices which are tamper-proof resistance, like hardware wallets, these are called. So to keep the keys on them. So the hardware wallets, then once you store the keys, you cannot copy them outside. So that's the beauty of it. So, but on the other hand, you need to have that device always. Okay, so let's look into a bit more into the wallet types. As I was telling you before, the wallets, either it's hardware or software and things like that. So they use two kind of strategies. Either non-deterministic keys wallet or deterministic keys wallet, right? So what is the difference between them? In case of non-deterministic key wallet, you have a bunch of keys. So that means you have K means each key contains bunch of each key contains public and private key. So what you do is in this non-deterministic wallet type, you generate 100, let's say 100 public private key pairs, and you use them for the transactions, right? So, and then again, there is no relation between the keys. Yeah. So this is a public private key, and this is a public private key. This is a public private key. So these are completely non-deterministic. So there is no relation between them. You just generate bunch of key pairs and as a starting point in the wallet, and you will use them as you want and things like that. When you run out of these keys, again, you can generate a bunch of keys and things like that. The second strategy is, it is called the deterministic wallet generation. As I told you before, so we use some seed information. You can say public key and private key generation information rather than keys, which you will use the seed information and use the seed information to generate a series of keys from it. And these keys are connected in somehow, and each one will contain public and private keys, and you can generate whenever based on need, you can generate a public key, or whenever you want to spend coins, you can generate private keys and things like that. This is called the hierarchical key generation, which we'll look into later. So what is non-deterministic wallets? A bit more into that. So for example, as I told you before, you generate bunch of keys randomly. So for example, if you download the original Bitcoin core client, so that means if you want to do Bitcoin transactions, or if you want to do Bitcoin mining and other kinds of things, you have to download a Bitcoin core client. So this is a piece of software which you download onto your laptop and things like that. When you download Bitcoin core client, what you get is you get 100 random private keys and public keys. right? So you will just generate this bunch of keys. And as I mentioned before, there is no relation between them. These are individual sets of keys. And the biggest problem is you have to store all these keys, right? It's not just sufficient to store some of the keys. You have to, let's say that if you have 100 keys you generated, and you have to save them, all the 100 private keys in a secure manner, so to spend the coins. So that means to back it up, you need to copy all the information. So that is the biggest advantage. And again, what is public private key? They use under interlaying elliptic curve cryptography. So this is the public key, and the small k is the private key, and things like that. To back it up, you need to copy the whole keys, whole set of keys, and things like that. In case of deterministic wallets, as I told you before, we use seeded information. These are called the seeded wallets. Any question? Yeah, let me open the chat. Okay, so these are called the seeded wallets. So basically, you have some seed information, and using the seed information, you will generate the series of keys. So what you have here is they use one-way hash functions, and you also have some kind of chain code, which is a random number, which you will use. And the advantage with this type of keys is then once you have the seed and the chain code and some other information, you can generate hundreds of keys, public keys, and you can get the coins transferred to those hundreds of public keys. And whenever you are in need, you want to spend or transfer those coins, you can use the seed information, and you can generate all the connected private keys. So that is how it works. And again, if you want to back up this whole wallet, you don't need to store all the keys. It is perfectly fine. You just store the seed information, and from the seed information, you can generate the whole set of keys. So unlike the previous strategy, where we have to store all the 100 keys, in this case, we don't need to store all the 100 keys. We just need to store the seed information. And using the hierarchical key generation technique, we will generate all the keys. We will generate all the public keys and private keys and stuff like that. Okay, a bit more into it. So in case of hierarchical key generation, so the most common format is BIP 32. What is BIP? Bitcoin Improvement Protocol 32, which is describes this hierarchical key generation and things like that. And this is one of the standard protocol. And again, you have much more other improvement protocols which follow much more, how can I say, secure or convenient protocols and things like that, but this is most commonly used. So this is how it works. You have some seed information, and from the seed information, you will generate the master keys, master public key and master private key, and which will use to generate child keys, right? Again, child keys is a set of master child private key and child public key, child private key and public key. And you can, from the child keys, again, you will generate set of keys. So you can say grandchildren keys, and you can generate the keys in a hierarchical manner like. In this way, you can, you can generate at least, you can say, a million of keys. If you need a million keys, then you can generate keys like this in a hierarchical fashion. And many times what people will do is they will use one branch of the keys. So for example, K0 keys and K0 grandchildren keys from the K0. They will use it for receiving the incoming payments, right? And the another set of the branch, for example, let's say KM3, and this branch is used for change addresses, right? So does grandchild, here is a question, does grandchild have any relation with the child or parent? Yes, they have. So I will talk about it later. So definitely they will have. They are not like orphans. You Let me put it like this: to generate a grandchildren keys, you need to have the parent keys. Parent keys means the immediate parents. So, for example, maybe let me show in the slide. So, if you want to generate the grandchildren keys from the top set of grandchildren keys, you need child keys of this one. So K0 or KM0. So that means you need connected keys. I will talk more about it in a couple of slides on that. So another important characteristics of using hierarchical key generation is that, let's say that you are a big company, right? So it's a big organization, and then what you do is you can generate keys like this in a hierarchical fashion, and you can use one branch of keys for each department. For example, the bottommost branch is used by the marketing, and the uppermost is used by the, for example, production department and things like that. So you will have different keys separated with according to the business function and something like that. Okay, let's go further. Okay, again, many times I was telling you before, we don't remember the keys in a old-fashioned way. That means we don't mug up or remember the keys using some hardcore memory deck, right? So what we do is we use mnemonic codes. So basically, mnemonic codes is nothing but some kind of set of words. So this is a nothing but standardized way of creating some English words. They are like this. For example, let's say that this is the seed key, seed information or seed key, you can say. And rather than remembering 0, C1, E2, and blah, 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 what you do is you convert them into mnemonic codes. Mnemonic codes is nothing but you have a dictionary of keys, and each value is mapped to a dictionary, right? So, and then this dictionary is containing some human understandable common words. So for example, army van, defense, carry, jealous, true, and things like that. You will remember those words. You will note down, you will copy these exact sequence of these words. And as long as you have the exact sequence of the word, you can convert them back to this key. So that is called the mnemonic code generation. So this is also called the mnemonic code generation, which is BIP 39 protocol. So this is a very common standard techniques. Again, remember, this key is in the hexadecimal format. So internally, what you have is you have a key like this. If you use this key in the hexadecimal format, then it is represented in the binary format like this. It is represented in the decimal format like this. And so it's a pretty big number, which you cannot remember. And so what we do is we convert into some mnemonic codes so that we can easily remember, and you can write this piece of the sequence of the words at a place and things like that. So most of the Bitcoin wallets and other cryptocurrencies as well, they use the standard import export functionality. So for example, if you want to back up your wallet, you just need this mnemonic code for backup of this mnemonic code. And when you go to move to a new device, and you will use this mnemonic code, so which will give you the seed key. And using the seed key, you can generate all the keys in a much more easy fashion. And before looking into the the mnemonic code generation and things like that, I just want to talk about the hardware wallets. As I was mentioning before, there is also hardware wallets which are used to store the keys. So these are like hardware. When once you store the keys, it is not possible to copy from it. So Treasure is one of the hardware wallet, Bitcoin hardware wallet. So you can just connect to the USB to that device, and it will when you start creating the wallet on it, it will give you the mnemonic code. So for example, here you can see it will display the codes, display the words. Probably you might not see clearly here. So it gives you a character and a word and things like that. You will note it down when you create the wallet. So this is the seed key for your wallet. And then whenever you initialize the wallet, and then you can do the transactions with them. So for example, if you want to transfer money, so you can simply press a button on it, and then it will generate the wallet and the transaction and other kinds of things. And when once the transaction is sent to the hardware device, you can sign that one. So signing means you need to use your private key. So that information you will connect your hardware device, and it will sign the transaction using the private key without getting the private key out of the this hardware wallet, and it will complete the transaction. So this is how this is like just a USB device which you connect to sign the transaction, and then you take it back. So this is why quite you can say quite secure, because there is no way you can copy the private keys from it. So people cannot hack this device. People cannot steal the key from this device. But the hardest limitation which you have the hardware wallet is you need to carry this with you. So if the hardware wallet is stolen, then you lost all the keys and things like that. Any questions so far? Okay, so let's go further. So what is this mnemonic code generation? So as I told you before, this is nothing but converting the keys into a human readable format, right? So mnemonic codes are nothing but the word sequences. So to represent a random number, which is used as a seed value for the wallet, you can say. And it's normally contain 12 to 24 words, depends upon the key size, the size of the seed word, or you can say seed key you want to use, and things like that. And it is easy for people to remember, and then you can take the backup, and using these backup words, you can again restore and back up your wallet. So this is how the mnemonic code generation works. So as I mentioned you before, we start with a random seed value, because this random seed value is the root for generating the private key info and public key info, which we will see in a bit of later and things like that. So create a random key with a min entropy. So that means with a quite big range of numbers, you can say. And this could be like 128-bit or 256-bit. So it depends upon the strength of the wallet you want and things like that. And then, so let us say that we take 128-bit example, right? So you have 128 bits key, random number generated. And then what you do is you will add 4 bits checksum. So basically, you divide 128 bits by 32. So it gives you 4. You will add the 4 bits checksum, and then it will become 132 bits, right? So it will, with the checksum bits, it will become 132. And then this 132 bit, what you do is you will divide into segments of each 11 bit. So that means you will divide into 11 bit each. So you will get 12 segments. So for example, 132 divided by 11, it will give you 12. 1, 2, 3, 4, and you have the 12 bits, right? 12 parts. And then when each part, what you do is you can take a value of each part and look into this dictionary. And the dictionary contains 2048 words. So that means it maps the value, each serial number to one word. So then you will look for example, if you have a bit containing this 11000, which is mapped to army, and then you will choose it. So basically, you convert this 128-bit seed word like this: army, van, defense, carry, jealous, true, and things like that. So you get a mnemonic word like this, right? So as I told you before, the seed word, the seed random number, it could be of different lengths. So for example, you can go for 160, 192, and things like that based on the number of the bits you want, entropy, and you can choose the checksum bits. Basically, why you want to use checksum bits? Because you want to get into a round partition numbers. So for example, if you have 128, you add 4, it will become 132, and 132 divided by 11, it will give you 12, right? So similarly here you have 160 and you add 5, 165 by 11, it will be 15. So it will make the rounding easier and things like that. So once you have these numeric words, right, then what you do is you use this tbkdf2 function. This is to say this is a kind of HMAC SHA-5226 function. This is some kind of cryptographic hash function with some more hardcore properties and things like that. So what you do is, once you have these seed words, and our next step is to prepare, our next step is to convert this into a 512-bit seed, which will be used for the key generation, right? So what we do is, we have this mnemonic code generation, which gives some value, right? And then we will add some salt. Again, why salt? So far what we have done here is, let me go one step backwards. So far what we have done is, we have generated a random number and we converted a random number into a mnemonic codes, right? So this is an auto-generated number. And salt will give you a opportunity to save some of your personal space, right? It's like a password on that, right? So you can choose a passphrase. So for example, a password for this key generation, and then it will be appended to mnemonic and then your passphrase, right? And then the whole thing is sent to this function, which will do the permutation and combinations for 48 rounds. It will do a lot of cryptographic operations. Finally, you will get a 512-bit seed word, right? So this 512-bit seed word is used for generating the public and private keys. That's what we will see later. Okay, so this is how the seed key is generated from the mnemonic words. So first you choose a entropy 128-bit entropy input. So this is a random number, and which is converted into mnemonic words. There is a question. I'm looking to the question. Why only after mnemonic it is added? Why not before mnemonic? Oh, you are talking about salt, right? Yeah. So let me go back here. So the question is, why we add salt here? Why not before, right? So the let us go back to one slide. What are we doing here? Here you choose a random sequence of 128 bits, and you are converting to some sort of the mnemonic, right? So here we don't use any salt because here the focus is to start with some random sequence and then convert into understandable format. But on the other hand, here we will add salt because this is a step before going to generate this 512-bit seed number, which is used for generation of the keys. So this is only place where you can add this passphrase kind of protection and things like that. So in the previous step, we are just converting we are just converting a randomly generated sequence into mnemonic code. So there you cannot use any salt and things like that. But here you can add that because it also offers allows multiple inputs and things like that. Okay, so here we have an example. This is the random sequence which we generate, and we convert into mnemonic words like this. And let's say that we don't choose any password. As I mentioned before, it will use this mnemonic as the salt word. Yeah. If you choose empty password, it will use this one, right? And then it will generate a seed 512-bit seed seed value like this, right? On the other hand, this is an example where you use password phrase diagram. So you have the same input 128-bit, and then it is converted into the same phrases, no change. And here I say I choose a passphrase, super duper secret, and this will be added to the keyword mnemonic, and then you will get a seed word, 512-bit seed word like this. Right? You can see this seed 512-bit is completely different now. And why do you need salt? Salt is like to use a passphrase gives two important features. It's like some kind of personal phrase, password which you put on the mnemonic words, right? Let's say that you have generated like this, right? You have the entropy, you have converted to mnemonic words and other things, and based on the mnemonic words, you generated this 512 seed. And let's say that you stored these mnemonic words, you wrote it in a piece of paper, and you put it in a safe free location and things like that. Then let us say that somebody has stolen that the piece of paper, and then they can get hold of the whole wallet. So that means they can steal all your coins and things like that. So having a salt will allow you to put a passphrase. So in this case, let's say that you have a passphrase which you will only remember. You don't write it on the paper and things like that, or you can also say that you store this passphrase in a separate location other than the writing these mnemonic phrases, codes and things like that. And let's say that some thief has stolen this one, and then he cannot generate the seed key because he also needs the passphrase, right? So if you only remember the password to yourself, then they cannot steal the coins and things like that. So having a passphrase will offer a second factor authentication. It's like the multi-factor authentication kind of thing, right? So but on the other hand, it is important to store the passphrase in a secure manner and don't forget it, right? If you forget the passphrase, then you are gone. Like all the keys, you cannot generate the keys, and the whole wallet is gone. So that is the important part. Okay, so let's quickly look into this hierarchy key generation. So I have been telling you that hierarchy key generation. So it is generated from the seed words. So again, we start with the same process here. We start with a pseudo random number. which is 128-bit, and we convert into a mnemonic word, and we add some salt at this stage, and that will pass to a HMAC SHA-52 function and things like that. And then it will give you as a 512-bit root key or something, or 512-bit seed key or something like that. And then what we do is we let's say this is the 512-bit seed key which we get in the previous steps, right? Yeah. So this is what we get output from all this processing 512-bit seed key. And once we have the 512-bit seed key, then what we do is we take the left 256 bits. So left half, you store it as the private key. And from the private key, we can recover we can create the public key. How do we do that? Using the elliptic cryptography, and you by multiplying the generator value, right? So you will get it like this. And you will use the right half of the 256 bits as the chain code. What is a chain code? Chain code is some sort of the seed word which you use to generate the children keys and things like that. So it works like this. You have the seed word, and you will generate the master keys like this. And the master keys will be used along with the chain code for the generation of the child keys and things like that. So here from the private key, you will generate the public key by multiplying with the generator value. Okay, so let's see how we derive the child private key, right? So this part we already have, right? So we started with the random number, and we ended with a seed word, 512-bit seed word, and we took left 256 for the private key generation, private and public key generation, and we used the right 256 bits as the chain code, right? So, and we got it from this previous step. And then now what we are trying to do is we will use this information to generate the children of keys for this one, right? So this is how it happens. You have the parent private key and parent public key from the previous step, right? And then we also have the parent chain code. The chain code is the one, you can say random number. You also have it. And then what you do is you will pass this index number. Let's say that you want to generate 100 child keys. Then you will pass one as the index number for the first key. And all this information is sent to the same HMAC 512 hash function. You have seen it before. So again, this will generate a 512 hash value. You will use the left 256 part for the child private key and child public key, and right 256 for the chain code. The chain code is, you can say, a random number which you need to pass each step and things like that. So you will continue this process continuously. So you have the parent private key and the seed, parent seed code and index number, and then you will generate like this. Okay, so why it is important? Knowing the child key does not make it possible to find its siblings unless you have the chain code. So the kind of security it offers here is, if you want to let's say that one of these keys leaked, right? So we have this key leaked by stolen by someone and things like that. Even if they have this key, they cannot simply do anything. They cannot guess what are the other sibling keys which you have and things like that. They also need the chain code. Unless they have the chain code, they cannot generate the keys and things like that. Okay, how many child keys you can generate? because here you are using a 32-bit index number, so you can easily generate up to 2 million. So this is 2 to the power of 32. So you can generate these these keys, number of child keys using this key pair, parent key pair, and things like that. So you can see here, you can like this, you can generate many keys and things like that. Repeating this process one level down, each key will be turned into multiple keys and things like that. So, and then every key will be used again. For example, this child key which we generate will be used to generate grandchildren keys. And yeah, it will be used to generate grandchildren keys. And again, it will be used further and things like that. So one more important step, one more important thing to note down is the keys which we generate using the hierarchical key generation, they are indistinguishable from the non-deterministic keys. So that means they look exactly the same as the other keys which we generate with the deterministic wallets, right? So in deterministic wallets, what we do is you generate a public private key pair, and in the key generation, you have some seed word information, seed keys, and things like that. Using that, you will generate the keys. But if you compare both the keys, they will be of the same length, they will be of the same format. So it is not possible to know whether a key is generated from the hierarchical key generation or whether it is generated from the normal elliptic curve cryptography using deterministic key and things like that. And because the derivation function is a one-way function, the child key cannot be used to find the parent key. Even if somebody stolen these keys, let's say all these three keys, right? The child private key and the child chain code. Let's say that some thief has this information. What they can do? They can hack the keys, which are derived from this child keys. So that means the grandchildren keys can be generated from this one. But on the other hand, it is not possible to generate the parent keys. So the parent keys are very secure. Since it's a one-way hash function, you cannot go back. So even if they hack partial child keys, they can only hack the keys generated from the child key, which are grandchildren keys or something like that. So any questions or comments? So this is what most of the wallets will use. So if you open a wallet in one of the cryptocurrency exchanges, what they do is they will use this sort of the key generation. And let's say that you have a wallet at some location with one company, one crypto exchange and things like that. Now you want to move to another crypto exchange. It's like you have an account in the State Bank, and now you want to move to Axis Bank or something like that. So similar to that process, when you want to move from one crypto exchange to other crypto exchange, you don't need to take all the backup and things like that. You can just take up the backup of the seed information, which is in the form of the mnemonic words, and you can use that to restore all the keys which you have in the another exchange or something like that. So it's so easy to back up and restore and things like that. So remember, again, if you lose this mnemonic word combination, and these new words has to be exactly in the same sequence, and if somebody steals it, and if you don't have a passphrase added as part of the salting phase, then they can get all the keys. They can generate all the keys from yourself and things like that. So let me stop here. And you have some extra slides. If you want, you can go through it, but these are like a much more, a bit hardcore, let me put it like this. like maybe much more secure, and for example in hardening keys and stuff like that. So normally you don't generate keys from the from 1 to 2 billion or something like that. On the other hand, you will generate keys with a very high index number and other kinds of things. So much more strategies to make it this is the hardening part and things like that. So you will go and generate in the last part of these keys, so that it's pretty big random number and things like that. Any questions or comments? So if you don't have any questions, then let us call it a day. And as I told you before, I have to leave at in 5 minutes. I'm giving a keynote in an institute of management at Vaisak. So, but let us meet next week. I think next Saturday we have the class again, and then we will continue the discussion. And I will also conduct a poll in the next class, just to understand how you are doing with the teaching and things like that, right? So basically, it's I want to gather is it understandable for you, and or is it all? Am I repeating the content which you already know and things like that? Just a small 3 to 4 questions poll, so that you can. I will just get how you are doing and things like that. Okay, guys. Bye. Have a nice rest of the weekend, and I will send these recordings later to Professor Shyamakar. Okay. Bye.
Yeah, thank you, Professor. Thank you so much.
Thank you.
I'll take, yeah. Students, please remain for 2 to 3 minutes. I need to give some announcement.
Yeah, I will leave now.
Yeah, you can stop the recording. Yeah, Professor. Yes.